Ladies and gentlemen, this is the medal lecture at the European Space Weather Week 2024. We are here in Coimbra, in Portugal, the very nice scenery. And it is a hybrid meeting, so we will have today lectures online and on site as well. So as well, some of you might have seen already, we had a medal ceremony yesterday, and we have 3 medalists, a Birkeland medal, a Nicolay medal, and a Krzyzewski medal. And we will have 3 talks relating to these medals. I have to say that our Nicolay medalist has unfortunately passed away a few weeks ago, so he cannot be present and he cannot give his talk, but his near colleague, Mark de Rosa, was very nice, and he will give a talk on behalf of him. So the name of the Nicolay medalist is Dr. Carolus Scriver. So that will be the 3rd talk. And I asked the Vice Chair of the Awards Committee to chair this session. So I call Nick Arch to the stage. Thank you.
Thank you. Welcome. Our first lecture is the Birkeland lecture, and unfortunately, the winner, Yoshizumi Miyoshi, wasn't able to attend because of complications with travel, but he's here with us virtually, and the title of his talk is Radiation Belt, Electron Acceleration and Scattering by Chorus Waves and Their Atmospheric Impacts. So the floor is yours, Professor Miyoshi.
Can you see my screen?
Yes.
Okay, thank you very much. My name is Yoshizumi from Nagoya University, Japan. I'm truly honored to receive such a distinguished award, the Birkeland Medal. Due to the plane accident in Japan, I'm pretty sorry that I was unable to attend the ceremony in person yesterday. But thanks to the effort of the Dr. Andrea Optics and the SOCLC members, I was able to join the award ceremony via Zoom. And I also feel incredibly honored to have this wonderful opportunity today. The title of this talk is The Radiation Belt Electron Acceleration and Scattering by the Ultramode Chorus Waves and Their Impacts. And today we are going to talk about the importance of the cross-energy coupling via the wave-particle interaction and its relationship to the solar wind drivers. Before starting this talk, so I'd like to briefly share the historical perspective on Japanese pioneer in space weather research. So he is a professor, Torahiko Terada. He's very famous physicist in Japan. And almost 100 years ago, he discovered such a fluctuation in the magnetometer near Tokyo. So nobody knows that at that time, but this is really the ULP-I2 pulsation, a plasma wave associated with the aura breakup. So this is the pioneer, the discovery of such a pulsation related to the aura. And also he gave the pretty famous word that naturally just described when we have forgotten about them. So the Terada considers earthquake, typhoon, and tsunami. Those are very popular disaster in Japan, but nowadays we have to consider the heat word for the space weather. Okay, so we like to start this talk. So this slide indicates the geospace system and radiation belts for the focusing today's topic. And this is the solar wind, and this is the magnetosphere, and this is the inner magnetosphere. And we can see the radiation belt, that this is the highest energy population in geospace, and the same region, so that we can see the 10 keV and 100 keV ions and electrons for the inherent, and the thermal dense plasma, the less than 10 eV, the 1 eV, the plasma sphere. So in the inner magnetosphere, the different energy population with 6 of that, from eV to MEP, the copy of this. And this is a collision-based system, so that the dynamical coupling of the different energy and region through the wave-particle interaction causes the evolution of the radiation of the belt. So this is the important concept. So the radiation belts, the electrons are very important for the species because the such electron causes the satellite discharging. So sometimes we see the Japanese newspaper that tell us the satellite anomaly. For example, the satellite broadcasting ring for the sumo wrestling was temporarily halted due to the satellite trouble, or the Japanese meteorological satellite was temporarily halted. So looking at the MEV electron data at the geosynchronous orbit, so we see the large flux enhancement of the MEV electron suggesting that some of the relationship to the such anomaly. So another important point is so the such relativistic electron causes the significant ionization, the middle atmosphere and upper atmosphere. So the particle precipitate causes the ionization, then the production of the NOx and the FOX, then we see the destruction of the ozone in the mesosphere and the upper stratosphere. So the such ionistic electron precipitation has really the impact on the neutral, the atmosphere. So in order to understand the dynamics of the radiation belt and the geospace system, so Japan launched the ISEE satellites 7 years ago, so 2016, and I am working the project scientist of this mission. So the satellite orbit is, the apogee altitude is about 6 RE, and the perigee is about 400 km altitude, and the inclination angle is 31 degrees. So we can look at the plasmasphere, the ring current, and the radiation belt from the ISEE observation, covering the wide magnetic latitude and L-shell region. And the satellite can measure the plasma particle for wide energy range from the 10 MeV to more than 4 MeV for electrons, and about 200 keV with mass discrimination for ions. And the field and the waves for the DC to the 10 MHz for the electric field, and 200 kHz for the magnetic field. So such a comprehensive data set will be very important to understand the dynamics of the radiation belt. Now we can look at the long-term observation, the ISEE measurement about the radiation belt from the 2017 to this year. This is the L-shell, and this is the time, and 500 keV, and 2.5 MeV electrons, and sunspot number, and DST. So ISEE satellite measure the declining phase of the cycle 24 and rising phase of the cycle 25, and we can see the recurrent type, the flux enhancement of the outer radiation belt, and also the semi-annual variation. And this flux enhancement happens in the very low L-shell region. So this event really early May this year. So we are very happy to tell you the satellite survived such a severe situation, and then the satellite provided us the very nice data. So, and also the ISEE satellite collaborated with the international satellite and ground-based observation, for example, the NASA Barnett probe, and the E-SWAN cluster, and the European Incoherent Scatter Radar ESCAT, and Super DAM, the magnetometer that other the ground-based network observation. Such the international collaboration pretty important to gain the science output, and we are very appreciate such the kind of consideration of the international colleagues. Thank you very much. Okay, from here we would like to talk about the relativistic electron flux enhancement. So firstly, we are interested in how the radiation belt flux response to the CME and CIR, those are main driver to cause the magnetic spokes. So this is a sketch to indicate the CME and CIR, so that we can see the high-speed solar wind and also the magnetic cloud. On the other hand, the CIR cases that we see the fluctuation of the IMF. So considering such the characteristics of solar wind, we have conducted a superposed analysis as a function of the F and time for the 8 days. So this is the CME storm and this is the CIR storm. And during the main phase, we see the dropout of the outer radiation belt, then the gradual increase during the recovery phase. So looking at these here, the CIR-driven storm are very effective to cause a large flux enhancement of the outer part of the outer radiation belt. And then we are interested in what solar wind parameter, the solar wind speed, or the IMF are important for the large so many, the coronal the stream event, about 200 events, then we discriminate the southward BT dominant cases and northward BT dominant cases by considering the Russell-Lafayette effect. So the solar wind speed for both cases is almost the same, the faster than 500 meters per second. But looking at southward BT cases and northward BT cases, that even with the high-speed solar wind, the radiation belt flux increases significantly when the average IMF is the southward, while it shows a little increase when it is south-northward. So that this result indicates the importance of the IMF PV to cause a large flux enhancement of the relativistic electrons, and also the Russell-Lafayette effect is very important for forecasting when the large flux enhancement will occur. Considering that this result, we develop probability the forecast algorithm to predict the flux enhancement of the relativistic electrons. And then we are interested in the physical processes that contribute the generation of the MED electrons. So the Richard Horn and other colleagues identify the wave particle interaction is very essential to generate the MED electrons inside the radiation belt. So this diagram indicates how the wave particle interaction is important. The Whistler model waves that generated the relativistic electrons, and the free energy source to generate the Whistler model wave is the 10 keV electrons, the hot component. And the thermal plasma population control everything to change the dispersion relation and resonance condition. So now the cross energy coupling, more than 6 orders from EB to MED, the completely really the essential to cause the large flux enhancement of the outer radiation belt. So considering the such the cross energy concept, we have proposed a model with the flux enhancement and solar wind structure. This is the solar wind speed profile and organic fluctuation indeed in the coronal stream, and such the organic fluctuation which the southward state causes the series of the substorm, the Hilker, and the Hilker causes the prolonged substorm activity is essential for continuous enhancement of hot electrons and wave particle interaction in the magnetosphere. Then we expect large flux enhancement due to the wave particle interaction. So that in order to confirm that this model, that we have conducted the superpositive analysis using the ISEE observation data. So actually we gathered many the coronal stream event for the ISEE, the observational interval. So this result a bit complicated, but this is the photoelectron population, the 10 keV electron, this is the source population for porous waves, and this is the porous waves, and the pseudo electron for the relativistic electrons, and the relativistic electrons. And this is the Earth, noon, dawn side, the dusk side, and night side. And this is the main phase, and the early recovery phase, and the late recovery phase. And looking at the early recovery phase, we see the shrink of the plasma pores, the equivalence becomes small, and the enhancement of source population and the force waves in the dawn side, and the gradual increase of the emitting electrons. And looking at the late recovery phase, the prolonged enhancement of source and the pseudo population can be seen, and enhancement porous waves over the local time, and the increase of the emitting electrons. So this result identified the prolonged substorm activity, the high-speed stream with the southward offset IMF is very essential for the continuous enhancement of hot electron, the pseudo electron, and porous waves. Then we see the enhancement of the LED electrons. So as the second topic of today's talk, so we'd like to talk about the impact of elastic electron precipitation into the atmosphere. So this sketch indicates the different energy precipitation into the upper atmosphere, the middle atmosphere. The 10 keV electron that causes the ionization, the thermospheric altitude, then we observe pulsating aura and diffuse aura. On the other hand, the multi-hundred keV and the electron precipitate into the mesosphere and upper stratosphere, and then the ionization takes place, and we see the production of the NOx and the ozone destruction. And very recently, we have proposed a model, so the unified model of the pulsating aurora and the relativistic electron microburst. So this conceptual sketch for the propagation of the Whistler model porous waves along the field line. So as mentioned by the Richard Horn the 2003 paper, that these porous waves propagate to the higher latitude, that these waves can resonate the 100 keV and MEV electrons. So the porous waves are generated near the equatorial plane, and firstly they resonate the 10 keV electrons, and we see the pulsating aurora. And then the porous waves that propagate the higher latitude can resonate with the 100 keV and MEV electron, then we see the microburst. So this is our test particle simulation of the precipitating electron due to the wave-particle interaction. So that this is the time, and this is the 10 keV, 100 keV, YMB, and we see the wide energy electron precipitation from a few keV to more than MeV. So the result indicate the relativistic electron microburst are high energy scale of the pulsating auroral electrons, and pulsating aurora may serve as a proxy of the relativistic electron precipitation. And the recent observation studied confirmed this model. And in order to understand how important such relativistic electron precipitation to the ozone destruction, that we have conducted the conjugate observation between the ISEE and the European incoherent scatter radar at unsafe altitude. And also that we collaborate with the Finnish colleagues, and then that we conducted ion chemistry simulation to evaluate how much ozone destruction takes place due to the relativistic electron precipitation. So this is the result of our conjugate observation for 4 hours. The top panel is the E-SWAN measurement, that this is a 60 km altitude and 100 km altitude, and during this interval, we see the significant ionization below the 70 km altitude. At the same time, we see the very strong ultraviolet wave and the elastic electron in the magnetosphere, and the computer simulation identified more than 10% ozone destruction happening at mesospheric altitude. So this result indicates that such elastic electron precipitation that actually causes the significant ozone depletion. And also, recently in the paper Birkeland, the Finnish colleagues, using the characteristic pulsating aurora as a proxy for the electron precipitation, so that he conducted the simulation for the global ozone depletion caused by the precipitation. But anyhow, this is a future challenge to understand how much ozone destruction takes place for the global scale. Okay, so this is the summary slide with the talk. So today we have talked about Sun-Earth connection via the wave-particle interaction, high-speed solar wind stream with the Southward IMF causes the continuous substorm, and prolonged ultraviolet wave generation, and acceleration of the MEV electrons, and precipitation of wide energy electron in the magnetosphere, and the precipitation into the atmosphere, and the mesospheric ozone destruction in the atmosphere. But this is the kind of the solar wind magnetosphere atmosphere that coupling the process. And today we have mentioned the cross energy coupling via the wave-particle interaction, the important role for the both generation and the MEV electrons and precipitation. Understanding the size of coupling with the plasma wave and the solar wind magnetosphere atmosphere coupling are really essential. And also we support as a future direction. So the continued observation is very essential because the variation of the radiation belt is quite diverse. And also the quantitably predicting the radiation belt, precipitation, and ozone depletion is also important. The ISEE extended mission is approved until March 2033, covering the cycle 25. So that we hope to contribute the further advancement in research. We look forward to collaborating with you. And before closing this presentation, I'd like to share another episode about Professor Terada. So Terada is also the famous essayist. And one of his famous essay is the death of the Professor B. And in this essay, Terada investigated the pulsation and discussed with the Professor B, who studied the child particle and aurora. So who is the Professor B? So Professor B is the Professor Birkeland, Christian Birkeland, the person after whom this award is named. So the Birkeland was enabled to return to Norway after his observation in Africa due to the World War I, and he decided to come to Japan to discuss his work with the Japanese scientists. And very unfortunately, he passed away in Tokyo. So I am deeply moved by the fact, even in the challenging circumstances of the war, Terada and Birkeland were able to collaborate 100 years ago, and I am deeply honored to receive an award bearing the name of the Professor Birkeland. I believe that in and I'd like to commit to the contributing to this field of the space weather research together with the international colleagues. Thank you very much.
Thank you for that wonderful lecture. I think we have time for at least one question. Are there any questions either online or in the audience? Okay, it doesn't look like apparently you were very clear. So anyway, thank you again for that wonderful lecture.